We are going to take an introduction here to nuclear physics, and we want to look at the basics of nuclear physics and what we need to learn in Physics 30, as well as the idea of the mass-energy equivalence. And we're going to use both of these concepts as we go through. So first of all, thinking back to this idea of nucleons. And Rutherford used his gold foil alpha particle scattering experiment, 1911 through 1913. Somebody counting flashes in the dark. He investigated the nature of atomic nuclei. Remember, we've got the alpha particles. He used polonium as his alpha particle source. They were fired through thin gold foil. And what he found is that some of them deflected significantly. This should all be reviewed. And figured from this that gold had a small, dense, and positively charged nucleus for each one. So using the same experiment, scientists investigated the nature of the gold nucleus and also other atoms. Zinc sulfide is a good detector because it'll flash, it'll get a green glow when it gets hit by an alpha particle. Henry Moseley used the scattering experiment to study nuclear charge for many different atoms. Okay, so nuclear charge, which we, because we haven't used Z for anything yet. So nuclear charge, which we call Z, was quantized. And he found that nuclear charge was always a multiple of the elementary charge. Rutherford called each quantum of charge in the nucleus a proton. We call them that as well. Periodic table is organized by increasing number of protons. So hydrogen has 1, helium has 2, lithium has 3, beryllium, boron, carbon, and so on. Counting up by 1, you can look at your periodic table. And that number, we call it sometimes atomic number, is also, oh, that didn't work, let's try again. We can also refer to that as Z. So for example, if I find on the periodic table Einsteinium. So if you don't have your periodic table out, pause it and get a periodic table out. When you find Einsteinium on your periodic table, you'll find that it is number 99. And Z is equal to 99 for Einsteinium. Okay, lovely. Which means it has 99 protons. The other result, though, that they found was that protons alone could not account for all of the mass of the nucleus. Moseley knew that the carbon nucleus had 6 protons because it had 6 elementary charges. But it had the mass of 12 protons. How could he account for this additional mass in the nucleus? Rutherford said that there must be another particle in the nucleus, and he called it a neutron. Neutron has no charge but the same mass, and it accounts for the additional mass. Existence of neutrons in the nucleus was verified by James Chadwick in 1934, so it took a while, but we got there. So modern day, there are 2 particles inside the nucleus. Protons and neutrons, they're in the nucleus, and so we call them nucleons. Lovely. Definition right there. So for the carbon-12 or C12 nucleus, they're not necessarily arranged exactly in a 2-dimensional circle. They're more spherical. Carbon has 6 protons and 6 neutrons, which means, of course, that is equal to 6. And the nucleus itself has a charge of positive 6. So there's 6 protons inside. And since neutrons have the same mass as protons, the carbon nucleus has a mass of 12 protons. So there's 3 parts of an atom, and we can describe them in terms of charge and mass. So our symbol for an electron is E minus, for a proton is P plus, for a neutron is N. And you should be able to find these symbols on your data sheet. It should be, if you look on the data sheet side, underparticles on the right-hand side. Maybe. As I look here, I think that might be the old data sheet that I am referring to. We definitely don't see the symbols there, but we should see electrons, protons, and neutrons there. Yeah, we don't have the symbols anymore. They've gotten rid of that for us. Easy enough to remember on these ones, though. Electrons are negatively charged, protons are positively charged, neutrons are neutrally charged. Right? And so, of course, this is the charge in terms of E, where E is equal to the elementary charge, 1.6 times 10 to the negative 19 coulombs. Notice that 1U in terms of the mass is 1.66 times 10 to the negative 27. That is not a typo. What that actually is showing us is that even though individual protons and neutrons have a specific mass of 1.67 times 10 to the negative 27, when they are inside our nucleus, they have a slightly smaller mass. We're going to talk about why that is. All right, we use nuclear notation, and this is more alphabet soup here. But X is the symbol of our element, right? A is the atomic mass number, or the number of nucleons, so basically protons plus neutrons, and Z is the nuclear charge, or the number of protons. So for example, for lithium-7, all right, lithium, there's our symbol, lovely. The 7 actually is telling us the number of nucleons, so that is our Z. And if we look, no, that is not our Z, my apologies. That is going to be our mass number. And then down here, we have the number of protons. This is our Z, which is going to be 3. All right, so we write the symbol. This is going through step by step. We write the mass number, or the number of nucleons, which, unlike what I just said, is not Z. And then we write the charge as, or the number of protons, which is the atomic number, or Z. All right. So looking at just this, we can fully describe the nucleus. We know that there are 7 nucleons. We know that there are 3 protons, and if we want to know how many neutrons, 7 minus 3 equals 4. Or A minus Z equals that, I guess, if you want a formula. So what about potassium-41? So here's our, what we have to do. So first, we want to write it out in nuclear notation. We want then to describe the number of protons, neutrons, and nucleons. We want the nuclear charge in coulombs and the total mass of the nucleons in kilograms. So from the periodic table, that's the easiest place to get this from. We've got an atomic number of 19, which tells us that this is the number of protons. And so that goes down here. From our question, we know that it is potassium-41, which means our mass number up there is 41. That's the total number of nucleons. So again, we have 41 nucleons, 19 of which are protons, and 41 minus 19 means we have 21 neutrons. Okay. Nuclear charge is determined by the number of protons. So I'm going to take my 19 protons, multiply that by the elementary charge, 19 times the 1.6 times 10 to the negative 19, and there's my answer. That's the charge on the nucleus in coulombs. And then the mass of the nucleons. So we can look at this in a couple different ways, but if we want to say, okay, there's 19 protons, 19 times the mass of a proton, which is on your data sheet, plus 22 times the mass of a neutron, also on your data sheet, and there it is. All right, so isotopes is another thing we got to talk about. You probably have heard about these in Science 10, Science 9, but it's been a while. So isotopes of an element have the same number of protons, but different numbers of neutrons. Because they have the same number of protons, they are the same element. That means that they have the same chemical properties, but because they have different numbers of neutrons, isotopes will have different masses. And at a nuclear level, that does mean if they have a different mass, we can use all kinds of different things, do things with them differently. They will have different nuclear properties. So for example, hydrogen, simplest element, has 3 isotopes. Okay, there's common hydrogen, which is basically just a proton by itself. We have hydrogen 2, so hydrogen 1 is the proton by itself. Hydrogen 2 is deuterium. This would be used in nuclear reactors to make heavy water. And sometimes it's like water is H2O chemically. Sometimes they'll actually, if they're using heavy water or deuterium to make heavy water, they'd actually refer to that as D2O. Just as a shorthand way of showing that this is water made with deuterium. You could drink, I wouldn't recommend drinking the water from the nuclear reactor, but if you had heavy water, you could definitely drink that. Tritium, H3, we could make water with that as well. It's pretty rare on Earth. There's lots of it in the sun, but not a ton of water on the sun. Spoiled the joke coming up. Yes, there we are. Yeah, most water on Earth is made with hydrogen 1. We can make water with hydrogen 2 or deuterium. It's a moderator in nuclear reactors. Most tritium that we would find is on the sun. We can make it on Earth. We could find it rarely, but most of it is in the sun. So it's also radioactive, half-life of 10 to 12 years. Both of these two are stable, which means we don't see any significant amount of decay. Hydrogen 3 is unstable. Half-life, we're going to talk more about that in a couple days, but half-life basically means that if I have a sample of, let's say, 1,000 molecules, within 10 to 12 years, half of them will have decayed to something else. And we'll talk about what those kinds of things would be coming up in a few days. All right. So one thing we got to figure out here is the stability of the nucleus. Protons are all positively charged, and they're very close together. And Fe is equal to KQ1 Q2 over R squared. When R squared gets very, very small, excuse me, what you're going to find is that this repulsive force, this Fe, is going to get really, really large. So why doesn't the nucleus just spontaneously fly apart? What force holds the nucleus together? And scientists have called this force, the force that holds the nucleus together, the strong nuclear force. Very creative right there. It's a strong force, so let's call it strong. It is always an attractive force, which makes sense. It holds the nucleus together. And it acts between any pair of nucleons, neutron, 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 proton, or proton, proton. And, you know, whether we said proton, neutron, or neutron, proton, that's the same. Order doesn't matter. All right. It is a short distance force. So it works only when the distances are very short. So if we're looking at, you know, just less than 1 times 10 to the negative 15 meters, super strong. By the time we get to 3 times 10 to the negative 15 meters, super weak. So it is the strongest force in nature, but it decreases dramatically with radius. Happily, we talk about it. We don't have to do a lot of calculations with it. A few basically looking to see if, as we look at bigger and bigger, we'll talk about this later on, but as we get to have bigger and bigger nuclei, the distance from one side to the other becomes big enough that sometimes the repulsive force overcomes the strong force because the distance just gets to be too big. All right. So anyways, There are really nearly an infinite number of combinations of neutrons and protons in the nucleus. Only about 400 isotopes have some degree of stability. There's thought to be this idea of islands of stability. So if we were to get to certain bigger numbers of protons and neutrons, that there would be somehow really stable elements that are really, really massive that we could theoretically make. If you look on your periodic table, basically anything like 104 and up, so rutherfordium, dubnium, seaborgium, borium, and so on, all of those have really short half-lives. They are very radioactive. And one of the things that you'll notice there is that in the bottom corner, they have a number in brackets. And that number in brackets is the most stable isotope, but usually they have a pretty short half-life. Okay, so they're quite radioactive. They decay to other things pretty quickly. In terms of isotope stability, we've got a line drawn on this graph where basically it's where n is equal to p. So the number of protons and the number of neutrons. And you'll notice for the first 20 or so neutrons, that stability, these are the stable isotopes, roughly follows that line, right? So there's some where we're a little bit below the line, so right, there. That means there's probably one or two less neutrons than protons, so more protons than neutrons. We've got this one here, right? More neutrons than protons. But then when we get to about z equals 20, so 20 protons, so everything above number 20, which is calcium, we start to see stability move away from being linear to being some kind of increase that's nonlinear. It's not, strictly speaking, quadratic, but it is not a linear increase anymore. Which is basically just what I said, roughly equal. There's equality, and you can have stability that are right around there. But if one increases more than the other, it tends to become somewhat unstable. So carbon 12, 6 protons, 6 neutrons, it's stable. But when Z gets bigger than 20, stable nuclei require more neutrons than protons. So lead, for example, lead 206. So on your periodic table, if you find lead, Pb, right, I would write the notation this way, and I'd find on my periodic table that lead is in number 82. Lead is going to have 124 neutrons in order to be stable. So there's 42 more neutrons than protons. So, question you might ask, and I kind of alluded to this earlier, why do large stable nuclei require more neutrons than protons? So, consider the protons on either side of the nucleus, right? Obviously, let's imagine this is a large nucleus, so there's lots of other protons. We're only showing these two here. All right, now, electrostatic repulsion is pushing them apart. The strong force is attracting them together, but they're far apart. They're, well, far apart in the nuclear sense. They are more than they're greater than 1 times 10 to the negative 15 meters apart. And so going back to that original graph of strong force and radius, it's not pulling them together all that well. So the electrostatic repulsion is bigger than the strong force, which means at this point, we're going to rip the nucleus in half, and we've got radioactive decay going to happen. But if we add more neutrons, now we increase the value, increase the magnitude of the strong force. We don't affect Fe, because they don't have any charge, but the strong nuclear force increases. And so, as you can see here, when Fe and Fs are balanced, the nucleus can be stable. But the bigger the nucleus, and therefore spatially the further apart the protons are, the more neutrons we need to have in the nucleus. All right, so that's the first half. If you need a break, you can take one. But as we move into the second bit on mass energy equivalence, you're going to want to make sure you have your calculator as well as your formula sheet. So let's go. Oh, let's actually go back to there and take a look at that. Classical theory, mass and energy are completely different. So something is either they have mass or they have energy. Usually mass would be things that are particles. Energy could be thought about in waves. But in the 20th century, early on even, scientists began to see that these were fundamentally related to each other. And scientists actually discovered that the actual mass of the nucleus was less than the total mass of the nucleons. So remember earlier, we found the mass of the nucleons, and I was careful with my wording, because the actual mass of the nucleus will be less than that. And the difference in mass is called the nuclear mass defect. So the equation here, this is really nuclear mass defect, delta M, is equal to the total nucleon mass minus the actual nuclear mass. Okay, let's take a look at that. What does that mean? So here's an example. Determine the nuclear mass of carbon-11 if its actual nuclear mass is 11.011433 U. Okay, so try it on your own first and then check out the solution. So if you want a hint to get you started, we want to find the total nucleon mass first, right? So delta M is equal to, in carbon-11, we have 6 protons and 5 neutrons. Now, the great thing about this here is this is carbon-11, and if you look on your data sheet, even though there's 6 protons and 5 neutrons, protons and neutrons have the same mass. So we can just go carbon-11, 11 times 1.67 times 10 to the negative 27, kilograms. Multiply that out, that's what we get here, 1.837 times 10 to the negative 26 kilograms. Now, for finding the nucleon mass, we use this value. Okay. So now, the actual nuclear mass is 11.011433 U. And when you're using with these actual masses, like the atomic mass unit, we use this value here. U is equal to 1.66 times 10 to the negative 27 kilograms. As far as I have looked on your data sheets, and now I just find it, I've looked so many times and never seen it, there it is. At your list of constants, the atomic mass unit, U is equal to 1.66 times 10 to the negative 27 kilograms. It is given to you. And so we would take the actual atomic nuclear mass, 11.011433 times U. So that number times 1.66 times 10 to the negative 27 kilograms, which gives us this. And now we want to take this number, circle it in red, this number, and subtract this number from it. Right, so delta M is equal to the total nucleon mass minus the actual nuclear mass. And we end up with mass defect of 9.1 times 10 to 9.10 times 10 to the negative 29 kilograms. And you might say, okay, maybe this is just a measurement error. But they kept having this error, and it's kind of like, what's going on here? What happened to that nuclear mass that was lost? Right? If the law of conservation of mass suddenly doesn't work, right? We already had Bohr, who had tried to get around the problem with orbiting electrons and saying, well, Maxwell's laws don't apply here. Is this something like that? And no. Einstein in 1905 proposed that mass simply is another form of energy, which means that the mass that was lost in the nucleus, called the nuclear mass defect, was simply converted to another form of energy, namely nuclear energy. So now we've got, instead of law of conservation of mass, we have the law of conservation of mass energy. And he calculated the amount of energy converted from mass using his most famous equation, E is equal to delta mc squared. Delta m is the mass defect in kilograms, c is the speed of light, and E is the energy converted from the mass defect in joules. So, new perspective on mass led to a new and more general conservation law, the law of conservation of mass energy. Law stated that the total mass and energy of a system remain constant during a nuclear reaction. So mass can convert to energy can convert to mass, but mass energy could not be created or destroyed. Turns out that nuclear physicists are more often interested in energy than mass when analyzing nuclear equations. Therefore, they developed a new unit for mass that would make it very easy for them to determine its equivalent energy. And the unit is called the electron volt per c squared. Yeah. We'll make it easy by making a miserable unit. Life goes on, we're going to learn how to use it. To illustrate this, let's consider how we're going to convert one atomic mass unit to the equivalent energy unit of mega electron volts per c squared. All right. So one atomic mass unit converted to this. Now, I'm going to go through this. I want you to pause as you go through and actually work through this. Do the math and write this stuff down. First, convert atomic mass units to kilograms. Okay, that's easy. 1U is equal to 1 times 1.66 times 10 to the negative 27. Right, that's on your data sheet. So 1U is equal to this, because 1 times something is that something. Lovely. Next, we're going to use Einstein's formula to convert this mass to equivalent energy. So E is equal to delta mc squared. So if this is my delta m, then that's the number I use for m. C squared is 3.00 times 10 to the 8th meters per second. We square it. And so that mass is going to turn into 1.494 times 10 to the negative 10 joules. And we will now convert that to mega electron volts. So first into electron volts, and this is the formula that we were using on Tuesday. 1.494 times 10 to the negative 10 joules. We'll multiply it by 1 electron volt per 1.6 times 10 to the negative 19 joules. Or I could also use the one that I showed you the other day, 494 times 10 to the negative 10 times 1.60 times 10 to the negative 19 electron volts per 1 joule. Either one works. And I end up with this. Hold on. All right, let's forget this little bit right here. Let's go back and fix my typo, which is right here, that this needs to have a negative sign in front of it. 1 electron volt per 1.6 times 10 to the negative 19 joules. This answer is correct. I'm just struggling today, apparently. And then we make our conversion, this one being correct, 1 mega electron volt per 1 times 10 to the 6 electron volts. We end up with 934 mega electron volts. And then finally use Einstein's formula again to put it into proper units. Delta M So delta M is equal to E over C squared. We're going to just go back and say, well, delta M that we started with was 1U is now equal to 934 electron volts. And I'm not going to actually substitute in the value for that. I'm just going to use C squared because that's the unit that I'm going to be using. So now I'm using the speed of light itself as a unit. And you'll notice if you look on your data sheets on the first generation fermions section, the mass is given in these units. Moving on. The value of this unit is that it tells how much energy will be liberated from mass. That is, if 1U, one atomic mass unit, is equal to 934 mega electron volts per C squared, then it means that if we convert all of that mass to energy, 934 mega electron volts would be liberated. And that's valuable information for nuclear physicists. And using that unit just helps them out. Continuing. Determine the nuclear mass defect in U that would convert 840 kilo electron volts of energy. So it would be required to convert to 840 kilo electron volts of energy. All right, so in this case, what are we going to do? Well, our formula, right, delta M is equal to E over C squared. And what are we going to do with this? Well, this is my energy. I'm going to need to turn that, first of all, into just electron volts. Let's take a look. And then once we've turned that into electron volts, we're going to turn that into joules. Okay. This is correct. And so that's going to be 1.344 times 10 to the negative 13 joules. We'll use the formula now to figure out how many kilograms that is, right? So delta M is going to equal that value, 1.344 times 10 to the negative 13 joules. Again, do the calculation, please. 3.00 times 10 to the 8th meters per second, and we'll square that. And so our mass is going to be 1.4933 times 10 to the negative 30 kilograms. We want to convert that into our atomic mass units. And so it's going to be, we're converting kilograms into U's, to these units. And what we're going to see is that this is going to be, we have our back to physics 20 unit conversion things, 1 U per 1.66 times 10 to the negative 27 kilograms. And we end up right here, 9.00 times 10 to the negative 4 U. Nuclear binding energy. So the actual mass of the nucleus is less than the total mass of its constituent nucleons. So with Einstein's equation, we now know this mass has been converted to nuclear energy, and that's associated, and it's called the binding energy of the nucleus. So two interpretations. This is the energy released when the protons and neutrons come together to form the nucleus, or we can say this is the energy required to break a nucleus apart. So we have to add that energy to set those neutrons and protons free. So let's look at the formation of helium-3. So constituent nucleons, there's going to be, this is helium-3 again, not hydrogen-3, 2 protons and a neutron. Okay, lovely. And here's our nucleus. Now, if we were to take a look at the mass of the of the nucleons themselves, all by themselves, 2 protons and 1 neutron, 3 times 1.67 times 10 to the negative 27, and there we go. So when it's the nucleons individually, we use the mass of each of those particles. In the nucleus, now we're going to say, well, the mass of this is 3U. So the mass is equal to 3U, which is equal to 3 times 1.66 times 10 to the negative 27 kilograms. And I think right quickly now you can see that this value with the 1.67 is going to be slightly bigger than this value with the 1.66. And indeed they are. Not by much. They'd round to the same. We're not going to round. And when the nucleus is formed, the mass decreases by not very much. 3.44 times 10 to the negative 30 kilograms. This is what we call the nuclear mass defect. So the one thing here, we've talked a lot throughout the course about significant digits. This is one place where we cannot round, like absolutely cannot round, because otherwise it just destroys this and we don't see this nuclear mass defect. Mass defect is converted to energy as predicted by Einstein's formula, E equals delta mc squared. So our delta m was this value here. C is there, squared. And we see that, okay, the nuclear mass defect multiplied by the speed of light squared gives us this many joules worth of binding energy. So energy that is released is called the binding energy for helium-3, right? So we've got these things put together are actually going to release energy. Okay, and this is why fusion reactions of small molecules anyways will release energy. More on that later. Let's reverse the process. Now, if we look at just the energy found in the particles here, this, right, just from the mass, well, this mass is less than this mass. Okay, we just figured that out. Where does the additional mass come from? We've got to add energy, right? So we have mass plus energy will give us this. And so we add 3.10 times 10 to the negative 13 joules. That's binding energy. We add that into the nucleus. That's going to cause the separation of the nucleons, and the energy converts to mass. All right, so determine the nuclear binding energy of cerium-140 if its actual mass is 139.905434 U. All right, so in this case, what do we want to look at? Well, we need to find the mass defect first, right? Right. So actual mass of the nucleus, that's given to us that many U, so it's going to be that number multiplied by our 1.66 times 10 to the negative 27. Here's the mass of our nucleus. Okay. Make sure you're working through this on your own. Don't just follow and watch. Constituent nucleons. We've got 58 protons, you know that from the periodic table, and 82 neutrons, or we can just say, guess what, it's going to be 140. 140 times 1.67 times 10 to the negative 27 is this number. Mass defect is going to be the mass of the nucleons, the latest one that we just got, minus the mass of the nucleus. Okay. And so the mass defect is this here. And put that into Einstein's formula. And we end up with, there's the binding energy, 1.40 times 10 to the negative 10 joules. Oops. Maybe. That is the end. All right, so there's going to be some questions you'll need to do with this. Please have them done for Monday. Thank you.